Hello, everybody. So we are now going into week 3 of remote learning, or we are now on week 13. So the last 3 weeks have been more fast-paced since we lost a week, but now we are back on track, so you can follow the regular pacing guide. I also posted a calendar for you guys, so you guys can keep track of what to do every day and what kind of video topics will be on YouTube for the day. So today we will be covering section 7.4, which covers graphing quadratic functions. So quadratic functions, they look like parabolas, so either like this, or like this, the ones that look like U's. Right? So before we get started with examples, I have some notes to talk to you guys about. So the first one is when graphs look like, so I guess before I talk about this, let's talk about the graph f of x, which is equal to x squared. This is a parent function. What is a parent function? A parent function is pretty much the simplest graph or simplest function of a version, like this version. Like for example, you'll go ahead and see for when f of x is equal to x squared, this is the most basic, but you can have so many different types of variations, like a and then x minus h quantity squared plus k. But we'll learn more about this later, but this essentially, it will still look like a parabola, just somewhere else on the graph. So what a parent function is so if we put in the points, so how do we graph a function? So if we're unsure how to, so we have our x and we have our f of x. So when you graph a parabola, you always have to put in 5 points. So I pick -2, -1, 0, 1, 2, right? And if I want to find the points of f of x or y, I just put wherever I see an x, I'm going to plug in -2. So -2 squared, this is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So our graph looks like this. So I'm going to make my pen bigger so I have more room for error. Oops, oh my gosh. Okay, well pretend, oh my goodness. Okay, let me try again. Maybe I'll start at the origin. So let's go up this way, kind of. Right, so roughly this is what the parent function looks like. Notice that this is curved, this is a U shape. It cannot look like a V. A V is absolute values, right? But we are talking about parabolas, quadratics. So now that you guys know what a parent function is, we can go ahead and start talking about graphs of f of x plus x squared plus k. So when it looks like x squared plus k, so like just adding a constant, it represents a vertical shift of our parent graph, f of x equals x squared. So if k is positive, then the graph of x squared plus k, it just shifts up k units, and if k is negative, then the graph will shift down k units. So it says absolute value of k because if k was equal to -3, you're going to shift down 3 units. You're not going to shift down -3 units. So you do want to shift down 3 units, right? So what does that look like? So I'm going to go ahead and put up our book here, right? So in example 1, so this is on page 613 of your textbook, we have this graph. So they added -3 and 3. It doesn't matter. You just need 5 points. But as you can see, the parent function, so these are the values, so you can see it's still 4, 1, 0, 1, 4. When you add 1, so when k is equal to 1, so what we do is for this y value, we're just going to add 1 more. So you can see 4 goes to 5, 1 goes to 2, 0 goes to 1, etc. Right? But so looking at h of x, which is x squared minus 2, we're going to shift down 2 units because there's a negative right here. And as you can see, if you compare to the parent function, you take the parent function and then you go down 2. So 4 goes to 2, 1 goes to -1, 0 goes to -2, so on and so forth. So I think it's really good to know the parent functions and what parent functions look like. Another example, so what else do I mean? I mean like the linear, like f of x equals x, it just looks like a line, and then we know that it can go up here, like it can do that, it can just be down here, right? So, but this black right here is the parent function, but there's just many different variations of it. Same thing with parabolas. So if you know this, okay, and then say that was like plus k, then this is going to be plus k. Right? If that confuses you a little bit, that's completely fine. You can still plug in, like if I put in -2 into here, -2 squared is 4, and I have plus k, so it's just 4 plus k. Right? You can still plug it in as you normally would. It's never wrong to plug in a point and get the output. Just like for graphing a linear function, there was a shortcut of using your slope and y-intercept, but some of you opted to plug in the points instead, which is completely fine, right? So now that we've talked about the vertical shift, we're going to talk about the horizontal shift. So it's when graphs look like f of x equals x minus h quantity squared. So that's a horizontal shift. Unlike the vertical shift, the horizontal shift is a little counterintuitive because when you see minus h, you're going to think, a lot of people think, okay, we got to move to the left h units. However, that's not right. So if you look at the note here, if h is greater than 0, then we're going to shift our graph h units to the right. If h is negative, then we shift our units to the left h. So if you look at the h, then yes, you move like so. If h is positive, we're gonna still move to the right. If h is negative, we're gonna move to the left. What makes it counterintuitive is that it looks like x minus h quantity squared. So when I look at this, so for example, if I had f of x is equal to x minus 3 quantity squared, h here is 3. But if f of x is equal to x plus 3 quantity squared, then h is -3. All right? So as long as you know that the base, that the horizontal, what it generally looks like, which is x minus h, okay? And then you know what, when h is positive and when h is negative, will be fine. So going back to our book, where examples, so I guess I didn't really show you, but like the black graph here was our parent function, and then the pink one is g of x, so you can tell that it goes up 1 unit. So all the points are, like, see, the graph is still the same shape, same everything, it's just shifted 1 unit up. And same thing for h of x, it goes down 2 units. So as you can see from the parent function, it does go down 2 units, all points. Right? So let's go to the horizontal. So that's page 615. And then you can look at this table and it talks about the horizontal shift. At x plus 1, h is equal to -1 because it's x minus -1. So therefore h is -1. And so as you can see, then you look at your x. Yes. Okay. So I guess it's harder to see here. This one would be a little different. So for example, you'd have to see, so x plus 1. So that means, I'm sorry, this is a little confusing, but I'm gonna roll with it. If you see that the parent function, f of x, is equal to 4 when x is -2. So because if you look at g of x, since it goes down, so since it shifts to the left, by 1, so that means -2 will go to -3, you will see that the y values match. Same thing, so that means if you look, all the y values shift up 1. So when x is -2, it becomes a value for -3. When x is 2, the value of 2 goes to 1, and so on and so forth. And same thing with x minus 2, h is +2. So for x minus equal to -4, then this y value will be for when x is equal to -2. Right? So you might need to look at this graph a little bit maybe to see it. But as you can see, the ones that they've graphed, the black one is still the parent function. And you'll notice for x plus 1, g of x, it does shift to the left 1 unit, and then for h of x, it shifts to the right 2 units. So even if I plugged in this, let's say x is equal to -1, x is equal to 0. If I plug it into g of x, I'll get 0 plus 1 quantity squared, and I'll get 1. So as you can see, you can still plug it in. It's not going to change anything. It's just if you know the parent graph, then you can do what I kind of explained. Right? But like I said, and I can't emphasize this enough, if you don't, if you're not comfortable with the little tricks, just keep plugging in the values, and then maybe eventually, once you do it enough, you'll pick up the patterns, and then you can just start doing it, no problem. Right? So one more thing, and then we'll talk about the general version. So we're going to talk about graphs with ax that look like a times x squared. So what this is talking about, it talks about either stretching or expanding f of x. There are tricks for this one, but for me, I'm actually not comfortable when it comes to stretching and shrinking. So what I do is I just plug in the values. When a is greater than 1, when a is not equal to 1, I just plug it in. I don't deal with the hassle. Right? But if you understand the trick, good for you, and you can do that. Right? So the first statement, so if a is greater than 0, the parabola opens upwards. So the first two statements of 1 and 2, I do look at a, and it tells me what, just kind of what direction will my graph look like. So for example, when we talked about linear functions, so something like ax, remember I told you guys, a technically would be the slope. So let's maybe change it to something we know better, mx, right? With m, remember if m was less than 0, our graph went down, and when m was greater than 0, our graph increased, right? And then m less than 0, it decreased. Same thing for this, ax squared. If a is greater than 0, our graph, our parabola, will go up like a cup. And then if a is negative, it goes down like a frown. And the way I remember that is when a is negative, negative Nancy, so they frown. That's just how I remember it. But for this, it actually goes into depth more. So if a is between 0 and 1, then the graph shrinks. If a is greater than 1, the graph stretches vertically. And then same thing for the bottom, right? But those are not as important. I just want you guys to focus on the very first statement of each one, knowing that if a is positive, it opens upward, and if it's negative, it opens downward, right? So I guess since you guys saw the other ones, what do vertical and horizontal shrinks look like? So in this case, so I don't know why they changed the colors, but this time f of x is pink. So as you can see, g of x is 2. So if we look over here, since a is greater, so 2 is greater than 1, you can tell that it stretches. So when it stretches, that means that the graph just gets skinnier. And then for h, a is 1/2, which is between 0 and 1. So it's a vertical shrink. So essentially when it means vertical shrink, it's just that the graph just gets wider, as you can see from these graphs. Right? So last thing I'm going to talk about before we start doing examples is just a general graph. F of x is equal to a times the quantity x minus h, quantity squared plus k. So what this essentially does is that it just combines all of these into just one general graph. So a has the same a still has the same meaning, h minus k is still your horizontal shift, and when you add k, it moves it vertically. All right, so this is a general graph of a quadratic. So, but it's still, no matter what type of version this is, it will always look like a parabola. So, what are the comments here? It says that the vertex is HK, but what is the vertex? The vertex is either your smallest value of the graph or the greatest value. It depends on A. So what do I mean? So if you look at this graph, the vertex is right here. This is the minimum, so this is the point where the numbers change. Over here in my drawing, the origin is our vertex. And then over here, our vertex is the maximum because it goes downwards. And then there's the axis of symmetry, which is the line x equals h. Right? So axis of symmetry, what does it mean? It means if we folded that dotted line in half, like along that dotted line, and we cut the trace, it would look exactly like both halves are the exact same. And so going to parabolas even further, so we have, oops, let me just go back to black. If we had f of x, and then this is x, okay, -2, -1, 0. Sorry, I'm going to go into the, oops, I don't even need that. If you notice, the absolute value, so 2 and its absolute value spit out the same y value. Even if I had like 3 and -3, if you saw in the example, they both equal 9. So if you just find the first 3 points, say 0, 1, 2, then you can just automatically tell me -1, say this is A and this is B. Oops, excuse me. -1 would be A and -2 would be B. Right? If you understand that, you can just go, you can do that. Save you some calculations. Right? And then 3 and 4, just what I said about about the vertex, about it being a minimum or a maximum. Right? But the value, so I guess one thing I should say is the value is y. It's your y value. Right? And then h is the point. Or actually, no, the point is hk, sorry. But it's at x equals to h. Right? So these are our notes, and then the next video we will start talking about examples of graphing functions.